Okay, thanks for having me again. Thanks for coming back. All right, today is going to be about Grothendieck, Witt, and L theory of Poincare categories. But before I do that, I want to give a very brief summary of the categorical properties that the objects that we discussed last time have. It's somewhat a painful theorem to state, but okay. So if you're ever interested in reading up details on this, there's a series of papers called Hermitian K-theory for stable infinity categories 1, 2, and 3. It's written by myself and 8 other people, so it's almost impossible to miss if you just Google me and find my website. Then, so I refer to any of these papers as #9 because there are too many people. And this theorem is proven in the first of these papers. And it says the following. So for one, there's the category of Poincare categories, and I already told you that it forgets, it's an inclusion into the category of Hermitian categories, and Hermitian categories forget to stable categories. I can just forget that I have a Hermitian structure. And the point about Poincare categories as opposed to Hermitian categories is that they equip the underlying category with a duality. Yes, that was the point. So this means that this composite factors through stable categories equipped with a duality, and in other words, that's a homotopy C2 fixed point for the action on stable categories that sends a stable category to its opposite. Yes. Okay. So an object in here you're allowed to think about as a category equipped with a duality. Okay. So that does something like C copper goes to C and then the duality of copper. Yes. From now on. Okay. So this is a commutative diagram. So last time I gave this kind of talk, somebody asked if it's a pullback. It's not, but think about it as an exercise. It's a commutative diagram. And the statement is that all functors that appear in this diagram have all adjoints. So that means every functor that appears has both a left and a right adjoint, and they're all explicit, is the statement. But I don't want to make them explicit today. It's not going to be relevant. I mean, I don't want to make all of them explicit. Let me say maybe in words, imagine you have a stable category. How do you produce a category with a Hermitian structure? Well, you just take the zero functor. What else could it possibly be? That turns out to be both left and right adjoint. If you have a stable category, how do you build a category that's canonically equivalent to its opposite? Well, you add its opposite to it. It comes with a canonical duality. If you have a category with a duality, how do you build a Poincare category? Well, you just do this homotopy C2 fixed point stuff on using the duality or orbits with the duality. So that orbit will be left adjoint, the fixed point stuff will be a right adjoint. And then this functor is a bit more complicated. It constructs, it uses a construction called the pairing category. It's just some explicit construction which you can make explicit in, you can always make explicit, but you can make even more explicit in particular examples. So let me just say that the adjoint going from here to here, both left and right adjoints agree, and they send a category C to what's called the hyperbolic category on C, which is C plus the opposite. And if you work out, you can do the exercise and do that adjoint and then that adjoint and work out what it is, but the concrete formula for the copper is sending a pair x, y to the spectrum of maps from x to y. Okay. That's what it is. So this functor is explicit, and let me say that these functors send C copper if this guy happens to be Poincare. In general, it's a bit more involved to say what for a general Hermitian category these values are of the right adjoint, but if you evaluate it by chance on something that is Poincare, then these arrows are both given by taking the metabolic category of C, either of copper or of a shifted copper. So I think the right adjoint has the sigma in and the left adjoint doesn't. I don't know. I just wanted to say that the explicit objects we saw last time, the metabolic category, it also arises as the value of some adjoint functor in this business, namely the adjoint of the forgetful functor from cut P to cut H, evaluated on a Poincare category. And evaluated on a general category, you have to do some slight modification of these metabolic things. Okay, so that's the statement. All of these constructions are explicit. In particular, I told you, I claimed that on cut P, the functor that takes a Poincare category to its space of Poincare objects is co-representable by some explicit category, this universal category. So if you run through these adjunctions and the corresponding statement that in cut H, the same category co-represents the form functor, as a consequence, you'll, for instance, find that Poincare objects in the metabolic category of C copper is equivalent to the space of forms in C copper. And this equivalence can be made explicit, and it's one instance of algebraic surgery. That's something I hinted at the very end of the last lecture, where I said this Q1 category sits inside MET, and then you can do some surgery, blah, blah. I forgot to tell you that this is an input you need for that. Apologies. But regardless, okay, this is just as to say that these constructions that we made have categorical meaning, and they, yes, this categorical meaning can be used to prove statements of this kind. Okay, so that's something that's true, and then here's a number of structural things that are correct. So cut H and cut P, they're both bicomplete. So they have all small limits and co-limits, and they're semi-additive. So semi-additive means that there is a zero object. The zero category with the zero functor has a unique map out and a unique map in. And there are finite direct sums. So there's a coproduct of finitely many terms, and there's also a product. There's a canonical map from the coproduct to the product, and that map is an isomorphism. So yeah, that's some categorical structure that will appear in a moment. Then both of these categories are canonically closed symmetric monoidal. In the best possible sense, so there is a symmetric monoidal structure on Hermitian categories, which restricts to a symmetric monoidal structure on Poincare categories. And closed means that there are internal Hom objects, so tensoring with a fixed object has a right adjoint, and the internal Hom objects between Poincare things happen to be Poincare. Okay, so it's just some nice multiplicative structures. And in particular, this implies formally that you can think of cut H as is cat enriched via the Herm functor from cut H to cut. Yeah, so I said there is a functor that takes a Hermitian category to a category of Hermitian forms. And any category that's closed symmetric monoidal is sort of canonically enriched over itself because you have the mapping objects there. And then you can apply this Herm functor to the mapping objects and you get mapping categories. And once you have a category that's cut enriched, you can talk about not only co-limits and limits, but tensors and co-tensors of objects. And we'll come to this potentially, I'll just say it. So these things are not too important for these lectures. I just want to put them on the board. Co-tensored over small categories. So that means whenever you have a small category, you can build a new Poincare category such that Hermitian functors out of that are determined by functors from your original category to the category of Hermitian functors. Okay, just some abstract blah blah that you can do. That's something that's sort of universally valid for cut H. Now with Poincare objects, you always have to be a bit more careful because you have this non-degeneracy condition. And it's just not true that if you take a Poincare category, you think of it as a Hermitian category and you co-tensor with something that the output will always be Poincare. It's just not correct. But so this restricts to co-tensoring, like in an, yeah, I don't know, on cat P, if maybe the small category I is the phase poset of a finite simplicial complex. And this fact, I think, was, first observed in this language by Jacob Lurie in his lectures on algebraic surgery theory. And sort of we took up his definition. So this definition of a Poincare category, I should have maybe said, is due to Jacob Lurie. And we sort of took up this definition and just expanded the theory to a full-fledged such a gadget. Okay, so that's something that you have, and that's, I think, useful to know. So taking this just for granted, it just means that we're very flexible in manipulating objects in there and constructing new objects from old. Yes, this is what all this categorical nonsense is telling you. Okay, so let's do this and define. Yes, please. Even bigger, yes. I don't mind. I'll try. Okay, so let C copper be Poincare. And then we define two things. I want to define a space called Grothendieck Witt of C copper, and I'll define it as the loop space of a geometricalization of a category that I'll call the cobordism category of C copper. And I'll explain in a moment more what this is, but informally you're allowed to think about this object as the cobordism category. Objects are Poincare objects. Okay, so let's say objects are Poincare objects in C and a shifted copper. I'll comment on this shift in a moment. And morphisms are cobordisms. And implicit in this business is the statement that you can compose cobordisms to a new cobordism, and so that ought to be a category. Yes, and that's the category you take. You take its geometric realization and the loop space at 0. Yes, 0 is a perfectly valid Poincare object. Okay, that's the definition. So the Grothendieck Witt space is a loop space on the cobordism category. And likewise, I want to define the L-theory space as not somehow built from the cobordism category, but rather what in geometry people have referred to as the cobordism spaces. So there's a procedure in geometric topology where people take a certain bordism theory, maybe of oriented manifolds or oriented PD complexes or whatever, and do a geometric construction to build a space whose homotopy groups are the cobordism groups. This is usually done by a so-called add construction, by using n-adds. So for that reason, I'll call it loops of the add construction on CQ. And I don't have an equally informal description of that thing as for here, but I'll tell you in a moment what this is more formally and what it is. But you're allowed to think of this as the analog of just cobordism space. The cobordism space. And so we ought to hope that this add. I'll explain it in a moment. Definition is about to come. So it's the cobordism space. All right. Yes, and as a reality check later, we hope that all the homotopy groups of this thing are explicitly described by generators and relations. Yes, please?
What is the category you mean?
There is no category. There is a space. I'll tell you what the space is. It's different, yes. Else, GW and L were the same, and they're not. Yes, I'll tell you in a moment. Okay. Say again. Where's the loop space? Where is it based? 0. 0 always makes sense, and it's yes. Okay. So more formally, yes. More formally, so the cobordism category of C copper is the category associated to the following complete simplicial Siegel space, complete Siegel. So I'll first write down what this simplicial space is. It's the space that takes N2, the space of Poincare objects in some category that's now called Qn of C copper. So now that is going to be a simplicial Poincare category. So this is a simplicial Poincare category, which turns out to be in the a complete Siegel object. If you know what this is, fine. If not, then it doesn't really matter. And it's defined as okay, let me informally say what it is first. So QNC copper, oh, sorry, there is a shift here. Okay, this shift comes from the fact that in the cobordism category, we think of copper as saying what is the dimension of objects, but in the cobordism category, the dimension is given by the morphisms and not by the objects. So if I say the objects, then I have to shift once, okay? So this is to adhere just convention in geometry. And so I'll just stick to this sigma throughout. And then in here, the objects look as follows. So maybe I have x0, x1. It's just n many composable cobordisms. That's what this is supposed to be. Okay? And now in order to explain to you how this is a simplicial object and what the Poincare structure is, it's just convenient to expand out these terms in pullbacks or throughout. Yes, so then you get a big diagram of this sort, but because everything is a pullback, it's really determined by these n composable things, and the statement is taking the big span is going to be the cobordism that you get. Okay, that's something you have to prove, but okay, fair enough. And the copper of such a gadget is just taking the limit over this diagram. So this diagram is indexed on something that's called the twisted arrow category of delta n, and then you apply copper to each term, and you take the limit over this diagram. Possibly there are some op missing, but okay. Okay, that's a formula for what this Qn is, and again, you're supposed to think about it as n composable cobordisms, and in fact, this condition that we take pullbacks here tells you that this category is, by the Siegel maps, equivalent to an n-fold Cartesian product over the 0 simplices of the 1 simplices. Yes, it's really just given by n many cobordisms. So that's a Siegel condition for that Poincare, simplicial Poincare category. And it turns out to satisfy some completeness condition. That is something that works. Okay, so in particular, this is a simplicial space, this copper Qn. Maybe I should also say this gadget here is a subcategory of C copper, and then you just take this cotensor with the twisted arrow category of delta n. Yes, this would be exactly those diagrams where you don't say that you have pullbacks. And you just take the subcategory in all such diagrams indexed over the twisted arrow category where you require these diagrams to be pullbacks, but you restrict the copper. And this is fully functorially in delta n, and you check that all the simplicial maps respect the fact that there are pullbacks here. Yes, please? Yes, I mean, if I do Q1, then I get the old Q1, and then a Poincare object in here will say that this guy is a cobordism between the two. That's correct. That's right. Yes, the simplicial Poincare category is complete, but if I apply functors to it, then it might not be complete anymore. Okay, so now I take the Poincare objects in it. The statement is this is then also complete, but it has to do with the fact that Poincare objects preserve all limits, and completeness is a limit condition, Siegelness is a limit condition. But this is sort of Poinc is a bit special here. It preserves all limits, in particular completeness. Okay, so this is what the cobordism category is more formally. It's a realization of Poincare objects of some simplicial gadget that you can formally build using these cotensors. Okay, and similarly, the add construction of CQ is also a simplicial Poincare category, whose n simplices are given by something else. It's often written as rho n of C sigma copper, and that is, it's a bit more simple. You take this and you cotensor with the phase poset of delta n. And now delta n is a finite simplicial complex, so that is in fact Poincare, and all the simplicial maps are Poincare and stuff. So this is a simplicial Poincare category to begin with. I don't have to make some slightly more complicated. No, these are simplicial Poincare categories, and then I apply, sorry. I guess you're right. So these constructions they construct simplicial Poincare categories, and then I'm allowed to apply Poincare objects. Then I get simplicial spaces. Okay, so this is now a simplicial space. And I can realize it, and I mean, taking these guys, these rho n's, the phase poset of delta n, and parametrizing objects with duality over them according to the dimension of the boundary components of delta n is sort of the way in geometry you can construct. Rho n is you take C sigma copper n, and then you take this cotensor with respect to the phase poset. So objects in here, for instance, for n equal let me do the two cases. N equals to 1. How does the face poset of delta 1 look like? It has two edges and one face in the middle. So here you'll see exactly the things we saw earlier. So secretly I'm saying that row 1 is Q1. And for n equals to 2, it expands out a little bit differently. So you have like 3 objects, and you have cobordisms between all of them. I don't know, A, B, C, and then you have something sitting in the middle. And the object satisfies sort of various kinds of dualities. And again, the copper structure on all of these terms is given just by taking a limit over this phase poset of delta n of copper applied to the diagram. Yes. So if you want to apply copper in this cotensor category to some diagram of this sort, you just apply copper pointwise and take a limit over the diagram. And
So now we should intuitively understand why the thing and the L thing captures different information.
yes, we'll do that now. Yes, but it's not so easy. But yes, but we'll do it now. So this is the statement. These are the constructions you can do. You do this Q stuff to build a cobordism category where the n simplicity are just n composable cobordisms. And you build the cobordism space by not taking composable cobordisms, but taking these adds, n adds of cobordisms, what is called in geometry. These things that are, objects with duality parametrized over the phase poset of delta n. Okay, so this is something you can do. And so here's a remark. There is a map of posets from Tn to the twisted arrow category of delta n. So the phase poset of Tn you can imagine as objects in here are non-empty subsets inside the set 0 to n. This is what the faces of the delta n are parameterized by. And the twisted arrow category of delta n has objects I less or equal to j, where I and j are between 0 and n. Yes, that's what the objects in the twisted arrow category are. Just objects are just morphisms. And so you can take this to the pair, which is given by the minimum of t and the maximum of t. That defines something, and you can restrict. Okay, so this cotensor is contravariantly functorial, right? Because you can restrict diagrams along this map. So you get a map from QNC sigma copper to rho n c sigma copper, and explicitly it does the following. So for n equals 0 and 1, well, Q0 and rho 0 are just both C, and the map is the identity. Q1 and rho 1 are both just the same, and the map is the identity. So map is the identity. But once n is greater or equals to 2, something happens, namely when n is 2, you can depict this as follows. So you have two composable cobordisms, 0, 0, 1, going to 1, 1, x 1, 2, going to x 2, 2, x 0, 2. Yes, so that's the datum you see in Q2. And now to this you have to associate a 2-add of things. And you do it by sort of collapsing, you do some sort of degenerate n-add. So what is the thing that you can guess you can do? I do the 3 output cobord, like the actual objects, the closed objects, I put on the corner of my simplex. So I should have x11 here, x22 here, say. Well, then I have a cobordism between x00 and x22, which is the composite cobordism. So here I can put x202. Here I should have x01. And here I should have x12. Wait, like this. And then I have to put something in the middle, but there's only one thing I can put there. It's x02, which is the identity here and the maps here. Okay? And you can expand out this thing always. Okay, it defines you something, but I think it's most instructive to think about it in the case n equals to 2. It takes two composable cobordisms to this sort of degenerate 2-add of objects. Okay? This is what it does. Okay. Okay. Yes, please. Yes, so in the cotensor of things, the Poincare structure is always the limit. Yes. Okay, so you see something. So this defines for you a map. So we get a map. Oops. From GWCQ to L theory of CQ. And in fact, let me point out directly that we get something slightly better, because we define both GW and L theory as loop spaces of something, and in fact, I described to you a loop map. Yes? In fact, a loop map. By construction. I've constructed something from the cobordism category to the cobordism space, and I loop it. Okay, and then you observe that, what is it you observe? I can evaluate this map sort of on pi minus 1. In other words, on pi 0 of the D-looped map. So I can look at pi 0 of the cobordism category, and I map it to pi 0 of the L theory space. And that map is an isomorphism. Why is that? Well, if you have a simplicial space, then the geometricalization, the pi 0, will be computed as like a co-equalizer of the two maps from the 1 simplices to the 0 simplices, but the map induces an iso on both 0 and 1 simplices. So surely I get an iso on pi 0. And in other words, you get what you expect, namely that the path components in the cobordism category are exactly the cobordism classes of objects. Cobordism classes of objects, of Poincare objects. Yes? Ah, sorry. Is this what you're confused about? Ah, thank you. Okay. Yes, absolutely right. The cobordism thing maps to the add space. L is the loop space of it. Okay. So this is cobordism classes of Poincare objects in C sigma copper. And here is an exercise. This is a group. Not very surprising, I suppose. We've already seen the fact that cobordism classes of manifolds should be a group by changing the orientation, and orientation changer we've implemented as putting a minus on the form. And so the task that you have to show is that if you have a Poincare object, that if you add to it the form with a minus, that this contains a null cobordism, or a Lagrangian, and the hint is to look at the diagonal inside this. The diagonal will be a, okay, so this is still an exercise for you to work out. But this is something we get. We have a comparison map between the cobordism space and the cobordism spectrum, the cobordism category, and the comparison map induces at the very least, an isomorphism on sort of pi minus 1, if you allow me to say this is pi minus 1 of GW. Okay. No, that's also true. Like, it's 0, in fact, in the case, yeah. That's why K-theory doesn't have a pi minus 1. Yes, the analog in K-theory would be that the cobordism category is the span category, and of course every object has a span to 0. Yeah, so the span category is connected. GW is not connected, and that, yeah, okay, so because you're asking, this comes exactly down, this will relate to the fact that Grothendieck Witt theory, even if it's sort of the analog of connective K-theory, is a non-connective theory. Yeah, it's this exact fact that the cobordism category is not connected, whereas the span category is connected. Okay, so what do we get? There's one further thing that we can observe, namely I can now look at Poincare objects of C copper. Yeah, Grothendieck Witt is supposed to have something to do with the fixed copper, and not with something else. What can I do? I can map that to Q1 of C copper, C sigma copper, by taking an object to the span like this. Yes, I think of a closed object as a cobordism from 0 to 0. And, well, this lands, by definition, in... okay, now I'm saying it badly, I suppose. Okay, so let me say this factors through. So if I now include this into the into its geometric realization, So this, okay, what is it I want to say? I want to say that this map implements a map to the cobordism category, and then the mapping space, oh, Jesus. The mapping space in the cobordism category from 0 to 0. Yes, this is what this construction gives me, because the mapping spaces in the cobordism category are related to Q1. Here I write down to you a morphism from 0 to 0. Yes, so I get a map from Poincare objects to the maps in the cobordism category from 0 to 0. As you would expect, a closed object is a cobordism between the empty set and the empty set. And of course, by realizing, this maps to the loop space of the realization of the cobordism category. Yes, here. No, not on the map, because the suspension comes from the fact that these objects have shifted duality, but the cobordism then has the correct. Yeah. I apologize for the shift, but it's made in a way such that the Poincare objects, by viewing them as endomorphisms of the 0 object, map to loop space of the cobordism category. That's sort of the way that you want it to be in geometry as well. So you have this canonical map, and that is GW. Yes? So you have a map from Poincare objects to GW. And then you can further go to L theory by this map that we've constructed. And you observe that both of these things, these are now group-like. These are groups in spaces. So I should add that there is a reason for why these things are a priori monoids, E-infinity monoids, commutative monoids, and it has to do with the fact that taking Poincare objects is a functor that preserves products, it preserves all limits, and cut P is semi-additive. So every object is, with respect to the Cartesian product, a commutative monoid, and any functor that preserves Cartesian products preserves commutative monoids. So all of these QNs are commutative monoids, and all the maps are maps of commutative monoids in the simplistic thing, and taking realizations of commutative monoids is still a commutative monoid, yes? So this is a commutative monoid by design, and this exercise tells you it's a group. So it's in fact a commutative group. And that tells me that in the very special case where I look at commutative rings that we cared about in the very beginning, so epsilon quadratic or epsilon symmetric forms over a ring R, more or less by design, they map into the Poincare objects of the category of perfect complexes on R with respect to this epsilon genuine quadratic or epsilon genuine symmetric structure. Yes, essentially these things are precisely the Poincare objects here whose underlying perfect complex is a projective module sitting in a single degree. Yes, that's essentially what this is. There's a canonical inclusion of this kind. And then you can move on to the Grothendieck Witt space of the same category. Epsilon genuine quadratic, genuine symmetric or something. And now we've observed this is a map. Okay, and also I should say this is a map of commutative monoids. This map is compatible with the direct sum operation. And this is a group. So by definition, this map factors to the group completion of the source. Yes, because the target is a group. And the group completion of the source in my introductory thing I just called epsilon quadratic or epsilon symmetric Grothendieck Witt theory of R. Yes? So note there's something you can associate to R, which is the group completion of unimodular forms, and there's something you can associate to categories. Grothendieck Witt as I described it to you, and there's a comparison map from forms to Grothendieck Witt of the category, and by formal nonsense it factors through a map from the group completion to here. And sort of one of the very important results in this whole business is the theorem of Hebestreit and Steimle, is that this map is an equivalence. That's also fine. I guess you're right. I wanted to say this is a group, and you're right that here it's irrelevant. Yeah. That was, of course, on purpose to see if you're paying attention. No, you're absolutely right. This is a group. It's an interesting observation to make, and it's irrelevant for the discussion here. Thank you. Okay, but the point is, if you are interested in group completion of Grothendieck Witt theory, which I will be in the latest lecture or in the next lecture, for sort of applications to geometric questions, or homological questions, say, then now we know what version of Poincare categories we have to put to calculate the correct thing. Yes, and the warning is that if I put this epsilon quadratic or epsilon symmetric without this genuine stuff here, where I just take naive homotopy fixed points or homotopy orbits, then in general this will just calculate something different. It's also an interesting object, but it's something different. And we can also analyze exactly what the difference is between the two, more or less. This is sort of the highlight I want to make. It's these non-abelian derived functors, these things that you say what happens on projectives, and then you extend to perfect complexes. Those are the ones that calculate the group completion. Okay, so let me say in words that this is sort of the Hermitian analog of a theorem that's probably referred to as the theorem of Gillet and Waldhausen, which would say that the group completion K-theory of a ring agrees with the K-theory of perfect complexes on a ring. So Gillet and Waldhausen prove something more general, but that is a theorem that's correct. This theorem is inspired by yet another geometric counterpart of this result, namely this analysis of Oscar Randall Williams and Søren Galatius on the homotopy type of the geometric cobordism category. So under certain assumptions, they describe this geometric realization of the geometric cobordism category as a group completion of B-diffs of manifolds. And this is the algebraic analog, and the proof they do is the exact analog of Oscar and Søren's argument. It's called parametrized algebraic surgery. So you sort of use parametrized surgery to simplify the homotopy type of this cobordism category, to make the objects become more and more connected, so as at the end to only see things that are cobordisms between 0 and 0, and then you check what the remaining B-diffs are, so to say. So this is an important result, and we should keep in mind that what I've tried to explain to you in more or less explicitly is that there is a comparison map. This is a well-defined thing now. And the complicated term is it's an isomorphism. And the tools involved in proving that this is an isomorphism are sort of an algebraic version of parametrized surgery theory. Okay, so that's good. This is something we have. So in order to continue and sort of make use of this thing, I want to understand how far, I mean, if ever I want to calculate something about Grothendieck Witt, I mean, it's good to have maps, but it's better to have maps whose fiber we understand somehow. Because if we have a map and we don't understand the fiber, I mean, what are we ever going to do? So to make sense of this, I'll have to give definitions. Okay, so I'll say that a pullback square, and I'll write that pullback square. Let me write it like this: C to C prime, copper prime, and a pullback square of this in cut P is called it's called a PV square. PV stands for Poincare-Verdier. Okay, and I mean here's, okay, I'm going to give you the shortest definition I know and then give examples rather than expanding too much on this. So what can I do? I can expand out this diagram with a 0 to the left and take the pullback. So maybe I call this functor P and this functor P prime. Then what I'll get here is the kernel of P, and which is equal to the kernel of P prime, because the diagram is a pullback. Yes. So these two kernels agree. It's just all the objects in C that go to 0 under P, or in C prime that go to 0 under P prime. And I just restrict the copper to this kernel. Okay? Something I can do. It's just the subcategory. And the fact that these functors preserve the duality tell me that the subcategory which is sent to 0 is closed under the duality, and then I can just restrict copper. Okay, that's something I can do. And now I can say that the left square and the big square are also co-Cartesian. Okay, that's the definition. Concretely, this just means that this object is obtained from this object by quotienting out by the kernel. Yes, I'm saying I take very specific pullback diagrams where, so to say, the vertical maps happen to be surjections. Like, well, that's a definition I can make. And I'll call it by split. So PV by split, PV if in addition P and P prime have left and right adjoints. Okay, that's a condition. A functor either has a left and right adjoint or not. In this Poincare world, it turns out if it has a left adjoint, it also has a right adjoint because the categories are equivalent to their opposites. But okay, the condition about bisplit things is what it is. Okay, and then with this definition given, we can say that a functor f from cut P, I'll say to spaces, but you could replace spaces with anything that has limits so that all the definitions make sense. And it's called, I'll call it additive if it sends split or bisplit PV squares to Cartesian squares. And I'll call it localizing if it sends the same thing but not bisplit. Yes, I think that's a legal definition. I'll call a functor Bordism invariant if f of CQ mapping to f of Q1 CQ, which is given by f of the cylinder construction, is an isomorphism. That means whenever I have a functorial cobordism between a cobordism between two functors, then I want the two functors to induce the same map on f of c. That's this definition, and I'll call it, if f is additive, I'll call it group-like if f of c copper is a commutative group in spaces for all c and q. Yes, so what I said earlier is an additive functor, it will preserve finite products. So the value on anything is at least a commutative monoid. And this might or might not be a group, and I call the functor group-like if all its values are groups rather than monoids. Okay, so yes, please. Yes? No. I mean, if P prime has the adjoints, then I think you're fine with P. But the other way around, I don't think so. Probably. Yes. Okay. So that's good. So let me give you examples. Some examples you've already seen. So what is a... Okay, let me say that a sequence where this guy is 0, or a square where this is 0, I call sequences. That makes sense? And it's easier to write down sequences. So we've done this thing. So this is the right boundary component, and this is this inclusion that sends x to x0. Yes. So that's a bisplit PV sequence. So it's probably not too difficult to guess what the adjoint of the evaluation on something could be. So I'll ask you to work this out. I should say that this being this thing being co-Cartesian in cut P means that D is the quotient by P, and it means for copper that this copper is obtained from this copper by left Kahn extension. And I'll just say in words that if you have adjoints, these Kahn extensions can be calculated by precomposition with the adjoints. We can work this out in the exercise session maybe to see why this really is bisplit. Yes, so you check the right adjoint, and then you check that the copper here is given by applying the adjoint and doing the copper here. This is the way you prove that this is so. Okay, that's one example. Here's another fun example. You will include the metabolic category into Q1 in the way we did. And that's, of course, ought to sit in something where I take, what was it? The left boundary component of Q1, then met is the kernel of this. And a similar argument as here shows that this is bisplit PV. And you can do something else, namely you can take C copper and map it via the cylinder, so the thing that's C XXX with the identities everywhere. And that's slightly more complicated, but it turns out that this sits in a split PV sequence with the hyperbolic category of C. So these are vertically and horizontally bisplit sequences.
What's the inclusion of the manifold?
Yes, it takes sort of L to X to the things where the one guy is 0. Objects with boundary as coordinates from empty to something. Yes, and then you observe that if you take the constant, sort of the cylinder, and you look at what is the boundary component of the cylinder, you get back what you had. So this map is the identity. And you get some map here. And in the very first thing I told you that hype is like both left and right adjoint to the forgetful functor from cut P to cut. So giving a functor from here to here, that's Poincare, really just says what happens on the underlying category. And on the underlying category, you just take L. Okay, you extract the Lagrangian out of a metabolic object. And that soups up to a Poincare functor to the hyperbolic thing. Okay, so that's fun. And here's an example of a non-split thing. So you can start out with perfect complexes on R. And you take your favorite, maybe genuine symmetric structure on it. And you take a multiplicative subset in R. And you localize. Yes, so you invert all the elements in S. And then you can take this genuine thing on RS. And up to a small error. So this need not be essentially surjective, so it cannot be really co-Cartesian, but you can just take the essential image, and then you're fine. Sometimes this is surjective, and then you're good. But up to this small thing of taking maybe a subcategory inside here, you can look at the kernel of this thing, and this kernel is often called perf R on S. It's just the elements that are supported on S. And you could restrict this genuine symmetric structure to this guy, included here. And this is a typically non-split PV sequence. Yeah, so those are kind of the things that are formal. I'd like to understand values on functors on the metabolic and the hyperbolic thing just to maneuver my way around like the theory. And those are the examples I care about in practice to calculate something. So these are the non-split ones typically. Okay, so this is what it is. These are some examples. Say again? Yes, that's C plus C op. And the quadratic functor sends a pair to the mapping spectrum. It's the right adjoint and the left adjoint of the forgetful functor from cut P to cut. Yes? Okay, so I mean... yes, I said sequences are the squares where this guy is 0. Yeah. Apologies. Sequences are the squares where this guy is 0. Some of those are the most important ones, but theoretically they're not sufficient to do the discussion. I have to officially say something about squares. And that's because, a diagram in spaces is not a pullback if the induced map on fibers is an isomorphism over a fixed point, unfortunately. So I have to work with Cartesian squares as opposed to fiber sequences. But the examples I can always build by putting a 0 here and then saying I have a PV square where one term is 0, and those I call sequences.
And what's the takeaway from these examples?
That things we've seen earlier, constructions and functors we've seen earlier, are instances of the definition I gave to you. And there are sort of ones that admit adjoints that sort of seem like formal manipulations within the constructions we do. And then there are things that don't have adjoints, which are maybe the ones that we care about later if I want to calculate something about Grothendieck Witt theory of Z. Maybe inverting some elements will help me and understanding what is fiber and co-fiber terms. Yes, so as I said, a functor from here to here is determined by... yes, okay, so you take this thing probably to L, and you apply to the duality in here to this thing, and then again extract that. So let me not do this in my head. But you take the dual, and again take the Lagrangian. It's probably some fiber of some map, and then yeah. It's a good exercise to work out later what the explicit formula for this on the second term is. The first term is L, and the second is the dual. Okay. Good, so these are examples. So here's an exercise that you can solve using only these examples. Or maybe I should also add the example that, okay, these are examples of such squares. And now, what functors have we seen? We haven't seen many functors. There's essentially only the functor of Poincare objects. There's not much more have we seen. And it is additive, and it's localizing because it just preserves all limits. Yes. And this is a pullback square with some additional properties. Of course, any functor that preserves pullbacks will send it to a Cartesian square. So the Poincare space functor is both additive and localizing. It's not Bordism invariant, because Poincare objects in C are just something different than cobordisms. What can I say? And it's not group-like, because the space of Poincare objects does not, I mean, there are no inverses, right? It's just not correct. If I have an object that's non-zero, I cannot possibly add anything on it so that it becomes zero. So it's a non-group-like functor that's localizing and not Bordism invariant. Okay, so this is what it is. Let me, yes, put an exercise on the board that is fun to work out, maybe, if I find something to erase with. I think we can do this, okay. Say again? Yes, or mine. I have one in my office. All my colleagues think I'm crazy. It's like every time it goes on anything. It's a cleaning company coming. Okay, so exercise. If F is additive and group-like, so it's an additive functor whose values happen to be groups, then you can show two things. On the one hand side, you can evaluate F on the metabolic category, and via this composite that Xander just asked about, compare it to F of the hyperbolic category. And you'll see that this map is an isomorphism. Although the metabolic category and the hyperbolic category, they look very different, but through the eyes of an additive and group-like functor, they're the same. Through the eyes of a non-group-like functor, they're not the same. Take Poinc. That's always the example you take. And then you just calculate what is Poinc on met and what is Poinc on hype. They're not the same. Poinc on hype is just the core of C. Poinc on map is objects in C with a form. That's what I said earlier. So, and there are non-zero forms on non-zero objects, so it's not the same. Unless copper is zero, in which case met turns out to be hype. Okay. Okay. So this is one thing, and the other thing is that you can check that a functor which is group-like and additive, that you can check that it's Bordism invariant if and only if its value on either the metabolic category or the hyperbolic category vanishes. See, copper, cat P, or F of hype C is 0 for all C in cut X. Yes? F additive and group-like. Additive, comma, group-like. Exactly. Yes? Okay, so the value on met and hype is the same, and either of them vanishes if and only if the functor is Bordism invariant, in the sense that it sends the cylinder inclusion into an isomorphism. Okay, so that's something good to have. And so let me finish today's lecture with the basic summary of, so this is one theorem, hashtag 9 paper 2, and it says that the functor that takes C copper to the realization of the cobordism category. This is a group-like functor by the exercise. Now it makes sense. And this is additive. Okay, so it means that the realization of the cobordism category, forming the realization of the cobordism category, sends these particular pullback squares, these bi-split PV squares, to Cartesian squares. And let me say that the main ingredient is something that we can try to make very explicit. It comes down to the following fact that if P from C copper to D and copper bar is such a P as in the definition, as in bisplit PV squares, then I can look at the fact of the actual cobordism category. Yes, this induces a map on cobordism categories. This is a functor of categories. And this functor is a bicartesian fibration. Yes, it's a bicartesian fibration of infinity categories, which means something to the fact that if you have a morphism here, there is a preferred and an object here that lifts an object in the source. There is a preferred way of lifting it to a morphism above, such that something on mapping spaces happens. It's something in this theory, and any such bicartesian fibration it's also what's called a realization fibration. So roughly speaking, what we're using here is that if you think about the cobordism category as the realization of Qn, then these Qn's are made in a way that they'll preserve these pullbacks. This is something you check explicitly. So somehow what you get is a simplicial object, which pointwise is a pullback diagram. You apply poink, remains pointwise a pullback diagram, but now you have to realize. And realization of simplicial spaces need not preserve pointwise pullback diagrams or fiber sequences, but it does so if the realization thing that you have is a good, it's a good map. And bicartesian fibrations are one of these things. You have a square, under certain assumptions, realizing it, you still get a fiber sequence. And this is sort of the incarnation. And this is a very geometric construction. Somehow imagine you have a morphism here that's a cobordism from somewhere to somewhere, and you have a lift of the one output of the cobordism. Then somehow you use the fact that for P you have good choices of lifts because you have both of these adjoints. And so then you lift the one span in the one direction and the other in the other, somehow. You do the only thing that you can, and that turns out to do the job for you. I mean, that's a very informal description. Of course, you have to give a formal proof. But I'm happy to sit down with you in the exercises later and try to write up what is like a co-Cartesian lift of this functor. Okay, so let me finish with the analog in the world of the add construction. That's due to Jacob Lurie. So the functor that's in C copper through the realization of the add construction, this is localizing. Yeah, so that's better than additive even. It's localizing. And the main reason is that add P from add C Q to add D Q bar, this is a Kahn fibration of simplicial spaces. Yes, and Kahn fibrations are even better, so to say. They also realize two fiber sequences with the correct fibers. Okay, so let me finish here. So this is what I wanted to say today. You have the cobordism category. It defines for you a GW space. You have this add construction. It defines for you an L space. There's a comparison map that you just explicitly write down. You observe that this comparison map induces an isomorphism, so to say, on pi minus 1. Yes, on this delooped object on pi 0. It's an iso. And these functors have favorable properties. This is still additive, and this functor is still localizing. And what we'll do tomorrow is we'll use this to calculate the fiber of the map from Grothendieck Witt to L in terms of algebraic K-theory. And then we'll use that to try to calculate Grothendieck Witt of Z from K-theory of Z and L-theory of Z. Yes, that's the game we're trying to play. Any questions about this? Okay, I'll finish here. Yes, please. Say what? What? Wait. Connective spectra, say yes. Ah. The statement was, take a functor to spaces which is additive, then it canonically lands inside commutative monoids. If it happens to land inside commutative groups, the statement is that this map is an equivalence of spaces. You can interpret it as saying, well, this functor is additive and takes values in connective spectra, and then this is an equivalence of connective spectra. But it's the same. These are formally equivalent statements, and both are correct. Absolutely. Yes. So yes, yes. The point is, you'll use these fiber sequences, and you'll show that. Yes. Yeah. Whenever you can check that a map is or that a diagram is a pullback diagram, whenever you can check it on fibers, you're good. And in group like E-infinity spaces, you can, because they're connective spectra. But it is as is, and if you replace f by a functor taking values in spectra or anything stable, you can forget about this, and the same result is correct, absolutely. Yes, we can discuss this when we prove this exercise. Then we'll see that what you say is correct. Yeah. Yes, there is an analog. It roughly speaking says that the L theory that you get for this genuine symmetric thing is Andrew's very first definition of symmetric L theory based on chain, like where the nth L group is given by chain complexes that sit in degree between 0 and n and come with a homotopy symmetric structure. This is the analog of the Hebestreit-Steimle theorem in L theory, and you can formally deduce this L theoretic statement from their result. If you want, sort of from their techniques, it sort of follows. But the L theoretic result is somehow easier. It's just an unparameterized surgery argument you can do, and that's what we do in paper 3. So the L theory statement is this genuine symmetric L theory can be described very explicitly. The L groups are given by certain objects with an explicitly described symmetric structure up to cobordism, as Andrew defined. And this you can just prove by hand without any parameterized surgery. Because the L space somehow, the fact that this is a Kahn fibration tells you that if D is 0, this is a Kahn simplicial space. So all of its homotopy groups have explicit combinatorial description. And then you just need to work one step at a time, and it's an unparameterized surgery argument you can do. So. Yeah? Ah, yes. That's a good question. So let's say for the quadratic thing, like this genuine quadratic forms. Okay, so the analog that you have to find is that what happens in algebraic K-theory is that there is one object that you can invert to get the group completion. Yes, and you just have to look at the stable automorphisms of that object. In forms that need not be true to the best of my knowledge. It's not clear if you have a general ring that there's a single form you can invert to get the group completion. But if this is true, for instance, for the integers, the groups that you will get are the isometry groups of something like hyperbolic forms or symplectic forms. Yes. So it's the symplectic groups or orthogonal groups over the integers that show up in this business. And those are the ones where we want to use this theory to calculate the mod 2 cohomology of. So before, that's sort of the one thing that we can add to this business. These, say, symplectic groups over the integers or orthogonal groups over the integers, they've been studied a lot. Rationally, sort of everything is known, like in the stable world, with finite coefficients different from 2. Karoubi calculated this when he defined Grothendieck Witt theory. This is sort of what he did it for. And then, sort of, because I think for this issue that, in their theory, 2 had to be invertible, because then all of these different variants, they are all the same, and so then they understood everything. But this materializes itself at saying that for the integers itself, you don't really know what happens at prime 2. And there was a conjecture of what it is in the symmetric case, and we confirmed that. And that's what I intend to indicate tomorrow, so how we get at that, and what actually then the cohomology of, say, the symplectic group with F2 coefficients is. The usual L theory of group rings, okay.
Wondering whether sort of random
Well, yeah, no, I mean, the surgery vibration of Quinn still involves actual manifolds, and we're doing sort of the algebraic things, but the L theory thing is going to be the same. I mean, up to some small issues. But if you work, say, with this homotopy quadratic or this homotopy symmetric structure, where you take chain complexes with C2 fixed points, then what Quinn wrote down was already compared to that kind of thing by Ranitzky, and our thing is just literally the same as Ranitzky's in this language. Now we're just allowed to apply it to different types of coppers, and what you obtain, for instance, is that you can also apply it to this guy, and you just get some spectrum that has, I mean, I'll explain to you how to get a spectrum rather than a space. It has homotopy groups, and then you just calculate what they are. And turn out to give you exactly what Andrew suggested what they should be. This is this fun fact that relates to what Mark asked. So for instance, Andrew said, the L theory of this guy ought to be something where the nth L group consists of chain complexes that have length n. They sort of projective modules sitting in an interval of length n with a certain structure on them. And that doesn't make sense when n is negative. What do I do? And then Andrew makes a remark in his paper. It's in one of these examples of his where he says, yeah, analyzing some fiber sequences, the correct negative groups will turn out to be that, and we'll discuss it at some place else. So this other place never appeared. I don't know what these fiber sequences are. I have no clue what happens. You take this object, you calculate its L groups. It's exactly what Andrew said, of course. Just, but I mean, it's there. It's predefinedly there, and you just get the right thing. Yeah.